Hi everyone, I'm Hanmei from UMass Amherst. Today I'm excited to introduce our work, NUMAlloc, a faster NUMA memory allocator. Uniform memory access, UMA, is a shared memory architecture where all processors share the same memory controller for accessing the memory. In this architecture, the access time to the memory is independent of which processor makes the request, so it's why it's called uniform memory access. However, as the number of CPU cores increases, this architecture is no longer scalable. To address this issue, NUMA architecture is proposed. Different from UMA, each processor has its own memory called local memory, and they are also be able to access other processors' memory called remote memory through the interconnect link. This process is called remote access, which is known as one of the notorious performance issues on NUMA architecture. A remote access is typically more than 2 times slower than a local access, thus hurts the performance. Our work tries to mitigate this issue on the memory allocator design. To reduce the remote accesses, some NUMA-aware allocators has been proposed. Their idea is simple: add a separate free list for each NUMA node and bind the memory to a physical node. In this design, the memory allocation requests are firstly served by the per thread free list, which is local, so it's log-free and quick. If not enough memory on the per thread free list, then they will track the per node free list. While these NUMA-aware allocators offer some advantages, they also come with limitations. First, thread migration, which happens when a thread moves from one node to another by the underlying operating system. This migration will turn all of the thread's local accesses to remote ones, thus hurt the performance. The second challenge is existing NUMA allocators cannot handle remote deallocation well. In this example, initially thread 1 requests an object from the memory pool, and then it waits on it for some time. The object is then passed to a remote thread, thread 2, and it also waits on this object for some time. Next, thread 2 finishes the processing on this object and wants to free this object, but the object was allocated by thread 1 on node 1 actually. Existing allocators typically will place this object on the deallocating thread's free list. In this case, it's thread 2's free list. However, thread 2 is running on node 2, which differs from the location where thread 1, the location where the object was located on. So there is a mismatch here. If thread 2 wants to allocate something in the future, it may utilize this object, resulting in many remote accesses. Third, huge pages can reduce the TL misses and improve the overall performance. But existing allocators work for huge pages with a lot of memory. Based on our observation, there's a gap between the granularity of allocated and used memory. A huge page has a size of 2 megabytes, but when a thread runs out of memory, it typically obtains a small bag from the per node free list. And in our case, one bag is only 32 kilobytes, significantly smaller than the page size. Assume there are multiple threads wants to allocate memory. Existing allocators will assign each thread with a different page, possibly due to a lack of thread location information. If they mistakenly letting 2 remote threads share one page, that will significantly impact the performance. Consequently, threads cannot share one page, resulting in substantial memory waste. To solve these challenges, we propose NUMAlloc, which includes binding-based memory management to address challenge 1, origin-aware memory management to address challenge 2, and incremental sharing to address challenge 3. I will introduce them one by one. Our binding-based memory management includes two types of binding, thread binding and memory binding. Thread binding means to bind each thread to a specific node during thread creation, so that no thread migration will happen. Actually, thread binding is not a new concept, and it has already been widely used. But our allocator is the first one that based on top of the binding, and we will show how much performance improvements can be obtained if the binding is considered within the allocator. Memory binding. In NUMAlloc, initially we will request a huge chunk of memory from OS and then divide it into evenly multiple regions. Each region is bound to a different NUMA node and file and by system call. This design makes NUMAlloc origin computable layout. That is, if we if given an address of a heap object, we can quickly compute the origin node of this object. For thread binding, NUMAlloc currently supports two types of binding. First, node interleaved binding, which means to bind the continuous thread to different nodes in an interleaved way so that each node will have a similar number of threads. Second, node saturated binding, and which will bind a sufficient number of threads to a node before binding to a new node. In this case, the thread to be assigned will be the same as the number of hardware cores on one node. NUMAlloc uses node interleaved binding by default. Additionally, users can also provide their customized binding file, a configuration file, to fit their workloads. Our binding-based memory management provides the following benefits. First, thread binding can eliminate the remote accesses caused by thread migration. Second, it enables us to obtain the origin of a thread without using expensive system calls, as threads are always staying at one node. This also works for the object, since our allocator adopts origin computable layout. Lastly, the combination of thread binding and memory binding inside the allocator provides a clear relationship between thread and memory. Therefore, it enables more advanced memory management, which I'm going to introduce. Origin-aware memory management also includes two parts. Both of them require the coordination of binding to make it effective. We have mentioned that our allocator uses an origin computable design, and so that we can quickly determine the origin of each heap object. Based on that, we propose origin-aware memory deallocation. When deallocating memory, we'll firstly check the origin of the object and the deallocating thread. If they are equal, then we will return the freed object to the deallocating thread freed, which is lock-free. However, if they are not equal, then the freed object will be returned to the free list of its original node. This design guarantees that a freed object will always be placed into a free list with the same origin as the allocating thread, which eliminates the remote accesses caused by remote deallocation and ensures the locality of the free list. In origin-aware memory allocation, when performing memory allocations, we will firstly check the per thread free list, since it doesn't require any locks and the object may still hit on cache. If there is no available memory on the per thread free list, then we will check these nodes this node's free list. If still fails, then we will allocate memory from the current node's unallocated area. And therefore, the local allocations are always guaranteed in our origin-aware memory management. Since our approach is based on thread binding, we can easily get location of each thread, thus allowing threads from the same node share the same page. We call this incremental sharing, as each thread only fetches the amount of memory it needs from the current page at that time, instead of the entire page. In this example, considering thread 1 and thread 2 are running on node 1 and thread 3 is running on node 2. Since thread 1 and 2 are running on the same node, they can safely share one huge page without any issue, thus reducing the memory waste. Therefore, our approach offers the best of both worlds by leveraging the performance benefits of huge pages without compromising the memory consumption. In summary, we propose NUMAlloc, which is based on binding. On top of it, we further introduce origin-aware memory management and incremental sharing. NUMAlloc also has other novel designs to improve the performance. Please refer to our paper for more details. Now let's talk about the evaluation. The evaluation was conducted on an 8-node machine, and we compare NUMAlloc with 7 state-of-the-art allocators, many of which are widely used commercial allocators. For performance compression, we evaluate these applications on parsec benchmarks, real-world applications, and Core 2 applications. In this figure, the runtime of different applications on each allocator is normalized to that of Linux default one. As shown in the figure, for almost all evaluated applications, NUMAlloc run the fastest. Only in few cases is slower, but only slightly. NUMAlloc has we highlight the application that with significant performance improvement. For the best case of the fully made application, we run 5.3 times faster than Linux default allocator. On average, NUMAlloc outperforms other allocators by about 16% and is 21% faster than Linux default allocator. What's the impact of each design choice on the overall performance? Let's start by examining thread binding. We cannot directly evaluate the thread binding on NUMAlloc, since other design choices like origin-aware deallocation and incremental sharing are based on it. So we evaluate thread binding on the TC-malloc and the Linux default allocator. The figure shows how much slowdown we will get if we disable the thread binding. As the figure shows, thread binding will significantly improve the performance of some applications, such as a float image and string cluster, and it does not hurt the performance of other evaluated applications. Overall, thread binding will benefit the performance, and we argue that it can be included in the memory allocator by default. We also evaluate the potential benefits of origin-aware deallocation. Based on the figure, we find it has obvious benefits for some applications. Overall, if we consider the origin of freed object, the applications can run 4% faster. Next, let's see the impact of incremental sharing on the application's memory usage. This table clearly indicates significant memory savings achieved with incremental sharing. Lastly, we compare NUMAlloc's memory consumption with Temeria, which is the current state-of-the-art huge page-aware allocator from Google. And currently, it is integrated into TC-malloc's code. We observe that the memory consumption of NUMAlloc is comparable to that of Temeria, just using a simple mechanism, incremental sharing. In summary, we propose NUMAlloc, a novel memory allocator designed specifically for NUMA architecture. On top of binding-based memory management, we further propose origin-aware memory management and incremental sharing, which makes NUMAlloc a faster and memory-efficient allocator for NUMA systems. Thank you for your listening. And is there any questions?
Okay, hi. So, this is Gary from NC State. So the first thread migration hurts performance of allocation, but obviously the reason you do it is because you want to improve the performance of the mutator, right? And
yeah.
It would seem like making use of otherwise unused cores, at least you do something with those cores. If you do it your way, you basically can't use the core because you'll be doing all non-local memory references because you can't migrate the memory, right?
Yes.
So the performance of the allocator alone is not sufficient in that case to determine the performance of the application, right? Because you can speed up allocation but slow down the mutator. Am I right?
So you mean I cannot prove the allocator's performance improvement?
If you bind memory to a particular location,
Yeah.
a particular, let's say, node, and then you've got processors over here, maybe in another cluster that have nothing to do, you can't migrate your memory there. The only way you can make use of them is if they make all non-local memory references. And I mean, the reason you migrate objects in the first place is you want to bring them closer to where they're being operated on to reduce the overhead of non-local memory references, right?
Sometimes maybe.
Okay,
Yeah.
so the performance statistics you gave seem to me apply only to the allocator and not to the application overall. Am I right about that?
Yes, we do the binding inside an allocator.
Right. So might it not be that allocating in that way makes the application, the mutator, slower? Because it can't move objects to where they're needed.
Yeah, that could be, but we argue that the binding can have some benefits that was overlooked by the previous study, and if the application, you know the application's behavior, you can also use some customized binding based on the knowledge of your knowledge on this application. So we still provide some flexibility for the users to make our allocator more fitable for their workloads.
I have a different question. The NUMA matters if the object is accessed from memory, and not so much if it's accessed from cache. Have you considered filtering objects for consideration, considering only objects that misses in cache?
So your question is, do I consider the cache?
Locality of the objects.
So you mean if do we consider the cache misses of our approach?
There's a NUMA locality, there's a cache locality. Cache locality would render NUMA locality irrelevant. You separate the two.
Yes, we haven't really considered the cache locality, but we have used perf to analyze the result of some applications, and some applications actually have better cache locality. but we haven't considered it in our allocator design. Thank you.
Any other questions? Last question.
So the benchmarks, are they all quite symmetric? I couldn't read all the definitions, so.
This slide.
So, like, how many kind of cores? So you're definitely hitting lots of different cores and different NUMA nodes in the system. Like, I just wonder what your experimental configuration is.
Oh, you mean the configurations of these applications?
Yeah.
The evaluation was conducted on an 8-node machine, so we try to, and each NUMA node has about 16 cores. So we use 16 multiplied by 8 threads. Make each application have 128 threads running. And this is also true for other allocators setting.
Okay, thank you once again.
Okay. Thank you.